Welcome back. This is part 2 of lesson 17. Okay, so you've now done exercise 7.2, so you've been practicing on this definition of basic solution, and you've seen that it relies on finding n active and linearly independent constraints. And the thing to really note there is that those are two separate ideas. The thing that you didn't have to do in 7.2 is you also had to make sure the solution satisfied all equality constraints, and that's because there were no equality constraints. Of course, in canonical form, we have equality constraints, and the really important thing is we're going to see how they add to the amount of active constraints. But then there's going to be this additional consideration of linear independence. Okay, so let's just refresh our memory on how canonical forms all have the same idea. So we're going to look at this example, and we're going to construct the matrix A. A is only going to be on the equality constraints. Okay, so this is the coefficient matrix. And what it is here, so we just look at these first three rows. There's these three equality constraints. So we'll say m equals 3. And here the matrix is 1, 1, 2, 4, 1, 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. And you should note that the number of columns is equal to the number of decision variables, and that's not coincidental. So there are n equals 5 decision variables. And each column of A corresponds to 1. This is the X column, this is the Y, this is S1, this is S2, and this is S3. And you can see how these columns line up in the constraints. Okay, not a coincidence. That's how that structure works. Okay, so then let's construct our C vector. I'm going to make it a column vector, which follows our conventions. I'll note that 3 and 8 are the first components, and then there's 3 zeros. Note that that's because you can rewrite this. This is equivalent to writing 0 times S1 plus 0 times S2 plus 0 times S3. And of course, we don't write 0 times these decision variables. We just leave them off. Okay, then the vector x of decision variables, which I'll put this little hat on, is then x, y, s1, s2, s3. Notice how the components of x have to line up carefully so they meet the arrangement of the columns in A and they meet the arrangement of the components of C. Finally, the B vector, again, this is just for the equality constraints. And it's 20, 9, 20. The knowledge that all the variables are non-negatives allows us to really not have to write down anything in particular for the non-negativity constraints. And all the inequalities here in canonical form, and I'm going to keep saying this, all the inequalities are non-negativity constraints on the variables. Okay, and we can see that that means that this model is equivalent to writing max C transpose X, so the dot product of C and X, remember, that's how we write that in matrix form, subject to the constraint AX equals B and X non-negative. If this form confuses you at all, please review the last lesson again and think about how the matrix multiplication works. Remember that for this particular case, this represents M equality constraints and this represents N non-negativity bounds. Okay. In this case, remember N is equal to 5 and M is equal to 3. Okay, so now let's start talking about how this works with our basic solution definition. So we're going to suppose X is a basic solution. How many linearly independent constraints must be active at X? Well, if we think about the definition, remember we say that N equals 5 must be active linearly independent. Okay, how many of these must be equality constraints and how many of these must be non-negativity bounds? And I'm going to break down this question as follows. At least 5 constraints must be active. All m, and in this case 3 equals 3 equality constraints. Remember, all equality constraints must be satisfied, which means they're active. Remember, for equality constraints only, to say they are satisfied is the same as saying they are active. So this equivalence is only true for equalities. Okay? And then at least n minus m, in this case that's 2. Remember, 5 minus 3 is 2. At least 2 non-negativity must also be active. Okay, and you can note that I've ignored the notion of linear independence so far. And that's going to play a crucial role as well, of course. This was misspelling independence. So I'm going to leave that as a question mark for this. We're going to address that here. If we have 1, 2, and 3 active, that means, remember, these are the equality. 6, well, what is 6? 6 is S1 is greater or equal to 0. 8 is S3 is greater or equal to 0. So these to be active, well, what does that mean? For a non-negativity to be active, this means these variables, S1 will equal S3 will equal 0. An active non-negativity constraint is the same as setting a variable equal to 0. That's a crucial thing I want you to keep in mind. It's one of those things that it's kind of easy to see when you look at the constraint, but it's something that I think students have tended to forget in the past. So I'd like us all to really take a moment to encode that. An active non-negativity constraint is the same as setting a variable to 0, okay? And of course, that's because S1 greater or equal to 0. If it's active, it means it's satisfied at equality. The same as S3 greater or equal to 0. If that's active, it means it's satisfied with equality. Note, that's why equality constraints, when they're active, it's the same thing as saying they're feasible. So all the equalities must be satisfied. And now we have these 2 non-negativity constraints also being active, so they're satisfied with equality. Well, what does that mean? That means to test for linear independence, we need to form the constraint matrix that form this system, that are composed of the coefficients of these constraints, and see if that determinant is non-zero, right? So let's see, what does that mean? That means that if we form this constraint matrix that just has these 5 constraints, that means we look at this matrix, I'll call it B. What is it? Well, it's 1, 4, 1, 0, 0. That's the first equality constraint. It's 1, 1, 0, 1, 0. That's the second equality constraint. Then 2, 3, 0, 0, 1. That's the third equality constraint. Now I need the S1 greater or equal to constraint. What does that look like? Well, that's just 0, 0, 1, 0, 0. And the third, and S3 greater or equal to 0 is 0, 0, 0, 0, 1. So make sure you understand how I got the coefficients for this matrix. So that's true. Now the determinant of this, I can use what's called the Laplace formula on the last two columns successively. What does the Laplace formula says? It says if I take this row and I'm going to multiply, the determinant is going to be equal to 0 times -1 to the 1 plus 5 times the determinant of this submatrix that would be formed by ignoring that column and row. I'll call that B11 or 5-1 to indicate that I've eliminated the fifth row and the first column. Okay, but that's just 0 times that, so that's going to actually zero out, and that's going to be true for all these 0 components because I'd have to continue and I have to say it's 0 times -1 to the 2 plus 5 power, but it's 0 times things, so it's going to zero it out. It's the determinant of B5-2. Okay, so that's true for all of these 4 components. They're all just zeroed out. So I'm not going to write the rest, but the one that isn't zeroed out is this last guy. And this is 1 times -1 so it's 1 times -1 to the 5 plus 5, so that's actually just 1, times the determinant of B5-5. Okay, well, what is that determinant? That's, I'm going to draw that, I'm going to put a green circle around that matrix, a green square, sorry, around that matrix. That's this matrix here. Okay, and then in blue, I'm going to circle that last row again, because all this stuff zeroes out. So then this is equal to, it's by the same argument, if you think about it, 0 times a -1 raised to some power times a subdeterminant, but it's 0. So the only thing that matters is, again, this 1 times the determinant, and I'm just going to write out the matrix that it's the determinant of. I have to be a little careful. I just realized I forgot the -1 part. It's actually not that important, the -1 part. And if you don't know why it's not that important, you should just think about the fact that we only care whether it's 0 or not, so the sign actually doesn't matter. But for, let's be careful. So it's going to be the 4th row, because remember, we're looking at this submatrix now. So it's the 4th row, the 3rd component. So it's actually the -1 is going to be there. So it'll be 4 plus 3 times the determinant now of this matrix. It's 1, 1, 2, 4, 1, 3, 0, 1, 0. Okay. Now, when I look at that, I could actually play the game again with the column using Laplace's formula again. However, what I'd like to do instead is to use MATLAB for this, to use Python for this. So to use Python for this, what we're going to do is, if you look at the lesson 17, BFS _ canonical .ipynb on Blackboard, you're going to see it's under this lesson 17. You're going to see that it shows you how to calculate out this determinant. Okay, it's in the first block there. And what we see is that determinant is actually equal to 5. So this whole determinant is equal to -5 because of the -1 from here. Okay, so we'll use that to calculate our determinants. And the reason why I did this is because the S1 and S3 are forced to be 0. Okay, right? So this is actually the system we are concerned with. And what we're really interested in is, does this system have a unique solution? And you can see that that is really the quicker way of figuring out what determinant to use is we just have to use the columns of the columns of A for variables not held at 0. Okay. And we already know this now. We know that the columns are linearly independent because this is the determinant now of this new matrix B. We know that's equal to 5, and that's not equal to 0. Okay, note that the addition of the columns just changed the sign from -5 to 5. Now, with this in mind, we can even write out and figure out the system. We can write out the system in a slightly different way. We know that S1 equals S3 equals 0. So the new system is actually this. It's just B times XY S2 equals the vector B. Right? And remember, the vector B here is equal to 20, 9, 20. Now, if you looked at that IPython, I actually showed a couple different ways that you can find that. The way that we might want to think about it is that because the determinant of B does not equal 0, that is the same thing as saying that B inverse exists. Remember, this is one of these many equivalent ideas to determinant not being equal to 0. A linear system has a solution. The rows are linearly independent. The columns are linearly independent. And again, when you look at that IPython notebook, it shows you what the B inverse is. Here, B inverse is -3/5, 0, 4/5, 2/5, 0, -1/5, 1/5, 1, -3/5. Note the common denominator here is the determinant. That's not a coincidence. And the solution to that system of linear equations is that x, y, s2 equals B inverse times B. So in this case, what that B inverse times B is equal to is 4, 4, 1. So putting all this together, the basic solution associated with 1, 2, 3, 6, and 8 is x, y, s1, s2, s3 equals 4, 4, 0, 1, 0. Okay, so that's the solution. Let's just generalize what just happened. Consider the generic canonical form. If it has m equality constraints and n decision variables, and we're going to assume that A has full row rank and m is less than or equal to n. If x is a basic solution, how many linearly independent constraints must be active at x? Well, there must be n. Right, that's just from the definition. Because x satisfies ax equals b, the number of non-negativity bounds that must be active must be n minus m. And that's at least. And we write that because now we have to check to see that the m columns corresponding to the variables that weren't part of these active non-negativity bounds must also be linearly independent. Okay, so we'll generalize that in this theorem. Note that this is saying that n minus m variables must be 0. So this is really where we get our theorem. If X is a basic solution of a canonical form LP, then there exists a set of m variables such that the columns of A corresponding to these m variables are linearly independent. The other n minus m variables are equal to 0. The real way I think this is useful to do is you set n minus m variables equal to 0. Check the other m variables have, that's part B, have linearly independent columns in A. And that's really A. Little a in the parentheses. Okay, so let's check your understanding of this theorem. Back in their example, what is n and what is m? So n, remember, equal to 5, m equal to 3. The variables corresponding to linearly independent columns of A were, and we're going to call these basic variables, but these variables were x, y, and S2 corresponded to linearly independent columns. S1 and S2 were fixed to 0. Okay. So given a basic solution X of a canonical form LP, we're going to say a variable is basic if it corresponds to one of these linearly independent columns of A that define X. And we'll call a variable non-basic if it is not basic, so and held to 0. Note there is a little thing here, which is that a variable could be basic and 0. Okay, so that it's just going to be the unique solution to the systems of linear equations, and of course sometimes that will be 0. And we're going to talk about that later. That means the solution has a property called degeneracy. We'll worry about that a little later. Anyway, in the basic solution X you computed on page 2, the variables that are basic are X, Y, and S2. And the variables that are basic are going to be S1 and S3. And the set of the basis, which is the set of basic variables, is just the set X, Y, and S2. Okay, that's the end of this lecture. I'd like you to now do exercise 7.16. You'll need that for the assessment. And I'm going to say this. So the assessment is asking a question which is answered with checkboxes. You can just rotely go through and you can, trial and error until you get it right. That will probably take a little less time than going through the exercise. Don't do that. Try to go through the exercise faithfully. Ask me questions if you have them. And this is going to really help your understanding of this. This is perhaps one of the most difficult lectures we've had so far. It combines many different definitions upon definitions upon definitions. I think the only thing that's going to get harder is maybe when we do duality. The importance of this exercise cannot be understated for understanding what we're going to do next when we start talking about the simplex method in full. Anyways, I look forward to your questions. Please ask them if you have.